Okay, we're going to start with this setup here. So this is obviously the pedal, and this is the back tire. And so imagine that the tech at the bike shop can turn the pedal with his hand, and when he does, then it will turn the back tire according to whatever gear it's set at. Okay, so just watch this. I'll go as slowly as I can. So that's one rotation of the pedal. So one rotation of the pedal is what angle of the pedal? He said 2 pi for the pedal. Agree with that? Angle of 2 pi, that's right. So for every 1 radian that the pedal turns, how many radians does the tire valve turn? Oh, by the way, just we got our terms straight, right? The pedal is the one on the left, the tire valve is on the right, okay? So for every 1 radian that the pedal turns, how many radians does the tire valve turn?
4.
What do you think?
It's like 4.
Okay, so I hear some people saying 4. So let me put the pedal valve at 1 radian. So that's one radian for the pedal. Does that feel like 4 radians for the tire valve? And if that's the case, then what angle of the pedal will we need for the tire valve to make 1 full rotation? What angle of the pedal will result in the tire making 1 full rotation? 2 pi over 4. Anybody else? What angle of the pedal will result in 1 full rotation of the tire valve? Okay, someone said 2 pi over 4, someone said pi over 2, which is the same angle. Agree? Pi over 2 is what part of the circle? 1/4 to the top. 1 rotation? Right, so that makes sense. So if the pedal, for every 1 radian that the pedal turns, that turns 4 radians, then it's going to take 1/4 circle for this to turn 1 circle, right? Okay, so this is the setup on page. In your workbook. This is page 288. Okay, page 288. So this is the scenario. For every 1 radian that the technician rotates the pedal, the wheel spins 4 radians. So for every 1 radian that they turn the pedal, the wheel spins 4 radians. Okay, so the first thing we want to do is write a function. Look at part C down below. Write a function f that's the horizontal distance of the pedal in radius lengths as a function of the angle of the pedal. So we're going to do that in blue. So we need a function of this pedal angle that gives us the horizontal distance of the pedal from the vertical diameter in radius lengths. We all should know how to write that function. What is that function? Sine theta. Agree with that? Have we learned anything in the last 2 weeks? Horizontal distance from the vertical diameter. Better know this. Better know this. Or else hit the books. It's cosine. Vertical distance above the horizontal diameter is sine. Horizontal distance to the left and right of the vertical diameter is cosine. And that's what they're saying. The vertical or horizontal distance to the left or to the right of the vertical diameter, and that's cosine. Write an expression to find the angle's rotation of the tire in terms of the rotation of the pedal. So we want the angle of tire valve. But that's going to be in terms of this angle theta. So what expression using theta would give us the tire valve angle? That's what we're asking here. And then part D. What expression of theta would give us the tire valve angle? We want the tire valve angle. We want the angle that's turned by the tire valve as a function of theta, the pedal angle. He said 4 theta. Agree with that? So the angle that the tire valve turns as an expression of the angle that the pedal turns. He said 4 theta. Agree with that or something else? Agree. It's always 4 times. We said for every 1 radian that the pedal turns, this will turn 4 radians. So that angle is always 4 times the pedal angle. So the angle of the pedal is just plain old theta. The angle of the tire valve is 4 times that, 4 theta. Okay, so now we want to write in E a function g that gives horizontal distance above to the right of the vertical diameter and radius lengths of the tire valve as a function of theta. So theta is going to be the input, but we want the output to be horizontal distance of the tire valve. What would that function be? Okay, he said 4 cosine theta and cosine 4 theta. Which one would it be? Right, cosine will give us horizontal distance. And so if we want it of the tire valve, then we need the tire valve angle in there. You see? What's the tire valve angle? 4 theta. Is it making sense so far? Okay. What angle of theta will cause the pedal to make a full rotation? What angle of theta will cause the pedal to make a full rotation? 2 pi, right? So 1 full rotation is 0 to 2 pi. Okay? What value of theta will cause what value of theta will cause the tire valve to make a full rotation? So watch for it. Tell me when to stop. What value of theta makes a full rotation? Right there. Full rotation is theta of pi over 2, right? Okay, and we can see that by, so 4 theta is called the argument of cosine, and in order for cosine, just as a function, to make a full rotation, the thing that goes into cosine must go through 0 to 2 pi. So for what value of theta does 4 theta reach 2 pi? Yeah, so it's confirming what we just said. So 4 theta needs to vary from 0 to 2 pi for this function to make a full cycle. And so we set 4 theta equal to 2 pi, and that tells us that theta needs to go to pi over 2 for 4 theta to reach 2 pi and for g to make a full cycle. So it agrees. Does it make sense? Okay, so then let's talk about what so if I were to graph f, can you sketch f? Quickly, can you sketch f in part G there, upper on page 289? Can you quickly make a sketch of f? You should be able to. That's the really easy one, right? So what will a graph of f look like, which is giving us horizontal distance of the pedal as a function of theta? Okay, so again, if you we've been over this, we went over it slowly. So that's the graph of f, basically the graph of cosine theta. At theta equals 0, we're 1 radius length to the right of the vertical diameter. That's why it starts at 1. So cosine's harder to see because we're graphing horizontal distance on the vertical axis, right? The output is horizontal distance, and output we graph vertically. That's why it's kind of harder to see. But we should be familiar with that. Okay, so when I do that, so that's the same graph. Okay, that's the same graph. What about the graph of g of theta? So imagine what the tire is doing as the pedal rotates. Now it's in red, it's going to form this function. Can you imagine what's going to happen? So remember, for every 1 radian that one turns, this one turns 4 radians. And we said that it's going to make a full rotation when theta equals pi over 2. So can you sketch that one? Can you sketch g of theta on the same graph? See if you can do it. So if this turns 4 radians for every 1 radian that turns, is the end of the period going to come sooner or later than 2 pi? Right, it's spinning a lot faster, so it's going to make it around the full. When is it going to make it a full way around? 2 pi? Pi over 2. So what will that graph look like? Okay, people are saying squished or really skinny. That's 1/4 rotation of theta results in a full rotation of the tire, or 4 theta. Half a rotation of the pedal means 2 times around for the tire valve, etc. Okay, so should make sense. So this, by multiplying by 4, Does it make the period longer or shorter? Makes it shorter, right? So by multiplying that angle by 4, it's sweeping up angles much faster than theta is, so it's going to make it around much sooner. It makes that period shorter. Does it make sense? Any questions on that? Okay, so while I'm setting up, go ahead and read number 5 and answer what you can on number 5 while I reset the animation here. So work on number 5, unless there's questions. Anyone have a question on this? Okay, so I'm going to reset. You start reading and working on number 5. Okay, so this angle theta over 2, or 1/2 theta, same thing. What does it represent in this situation? That expression, 1/2 theta. What quantity is that? Okay, it's 1/2 the pedal rotation, that's true. Yeah. Half of the number of radians, that's true. But in the context here with the bicycle, what does that as a whole, the 1/2 theta, what does it represent?
The angle swept by the tire valve.
He wants the angle swept by the tire valve. What indicates that this function h is about the tire valve? What is it about this that indicates that it's about the tire valve? Okay, that's true. That's true. There's something else about that's true. That's true. There's something else about it that's kind of saying, I'm about the tire valve. I'm about the tire valve. Okay, that's the same thing.
12.5.
What's 12.5?
Radians.
Yeah, see, that's the distance. I don't know. Maybe we kind of skipped over that. Does it say there? Yeah, so in 4b, it says the tire valve is 12.5 inches from the center of the wheel's rotation. It says the tire valve is 12.5 inches from the center of the tire's rotation. So that's a kind of a big clue here that this is about the tire valve, and therefore 1/2 theta is what?
So for every half of the pedal sweeps, the tire goes 1/2.
Okay, but what is 1/2 theta? What is that quantity? Some of you said it. It's the angle swept by the tire valve. If this is something to do with the tire valve, then that angle is the angle swept by the tire valve. Because of this 12.5, it's just a big clue. We're not 100% sure, but we're kind of 99% sure.
But you know it's just theta. But isn't the angle theta? So it's just say like theta.
What's theta? What angle is theta? No, it's not 1/2. What does the quantity, the theta angle mean? What is it? Which angle is that? The pedal angle, right? Theta is the pedal angle. Okay, so theta is the angles counterclockwise from the 3 o'clock position.
Although 12.5 lets us know that it's the tire.
Yeah, because that radius from the center of the tire to out to the tire valve is 12.5 inches. It's kind of like a big clue. It's like, oh, okay, this function's about the tire. But it's kind of like we're 99% sure. There's no guarantee. Okay. But in the context, it's kind of like, what else could it be? So angle swept by the pedal counterclockwise from 3 o'clock. That's theta. And so then 1/2 theta is our tire valve angle. Again, counterclockwise from 3 o'clock. All right. So just in general then, how is the tire turning relative to the pedal? He said slower. Agree? Can you be more specific? Anybody else? What's that?
Isn't it turning the same speed, but since it has a longer radius measure,
Are they turning the same speed? If theta is the angle swept by the pedal and 1/2 theta is the angle swept by the tire valve, are they turning at the same speed? Half the speed, right? So when I go halfway around with the pedal, how far will the tire valve go? A quarter. And when I go all the way around with the pedal, halfway, right? So it's the angles being swept, that's exactly what it is. The angle being swept by the tire valve is always half of the angle swept by the pedal. It's always half. So to get all the way around with the tire valve, is that going to take more or less than 2 pi of the pedal for the tire valve to make it all the way around? It's going to take more, right? It's going to take more. So that period's going to be longer or shorter? Longer, right? So now, in order for sine to make a full rotation or a full revolution, that takes what? What does 1/2 theta need to do for the tire to make a full revolution? Go from 0 to what? 1/2 theta needs to go to 2 pi, because 1/2 theta is the argument into sine. And whenever the argument makes it to 2 pi, we get a full cycle. So therefore, what is the period? So we're saying when 1/2 theta reaches 2 pi, that tire valve's made it all the way around. So what does the pedal need to do so the tire valve makes it all the way around? 4 pi. We need 2 rotations of the pedal, or 4 pi, to get 1. Okay, so sketch both graphs. Does it say sketch them both? What are we on here? So on F, so ignore the instructions, we're going to sketch both. So, no, sorry, we will follow the instructions. So here's the, let's see, what do I want? So now we want, this is vertical distance, right? So here's our vertical distance for the pedal. Okay, so I'll repeat it over there. So now the question is, what will this function, how would you sketch h compared to just the plain vertical distance of the pedal? So what will the h graph look like, which is graphing vertical distance of the tire valve in inches as a function of the pedal angle? So what will it look like? See if you can do it. You can graph sketch them both on F there on the middle of page 290. So can anyone describe what it's going to be like in the end? What's that? He says it's going to be wider. Agree with that? So the period's going to be longer or shorter? It's going to be longer. The period is going to be, it's going to take more theta to get this thing all the way around. How much more? Out to where? 4 pi. So it's going to take 4 pi of the pedal angle for that tire valve to make a full rotation. And that's our period, right? That's what we found. The period was 4 pi. Okay, anybody have a question? Does this make sense? So before we were talking about changing the argument as an expression of time. But this is also valid too. The argument can be another angle. Right? So we have the original input angle, which is here being represented here by the pedal. And then your expression of the argument can be some other angle rather than an expression of time. Okay? So this is just another way we can look at these functions. Instead of having the argument be as a function, expression of time, the argument can be another angle, which in this case is the tire valve angle. Can I erase this? We're good. So let's take a look at this sinusoidal function is any sine or cosine function. Okay, any sine or cosine function. So it can be multiplied by the radius. It can have a different argument, but any sine or cosine function is sinusoidal. So how are we defining what the period is? Remember how we define what the period is. Let's review that. So here's a sinusoidal function. So what is the period? Is the period like the distance from here to here? Is that the period? How about the distance from the bottom to the top? No. Is it the width of, say, the valley there? Okay, so what is the period? I'm giving you some choices there. Can you describe what the period is?
Like the time on the x-axis required for the function to go from positive to negative.
From positive to negative.
Or negative to positive.
Or negative to positive. Okay, so he said, first of all, it's like an interval width on this axis. Agree with that? Yeah, so your period it's an interval width of input. It's an interval width of input. So that, what would happen?
The length of one wave repeat.
Yeah, so we call it a cycle, right? So from here, tell me where the period ends here. There. Okay, you could also measure it, say, from here to, tell me when to stop. There, okay? That would also be a measurement of the period. So it's an interval width of input values that corresponds to a full cycle of output. Okay, so here's just our basic cosine function. What's the input? What's the input? Theta, right? Angle swept counterclockwise from 3 o'clock. What's the output? Okay? The output would be cosine theta, or horizontal distance right of the vertical diameter. What's the argument? Also theta. What's the period of cosine theta? 2 pi, and that's the key. The argument for cosine, when the argument goes through when the argument varies from 0 to 2 pi, or any interval width of 2 pi, f, that's the period, f experiences 1 cycle. And that's how we find the period for more complicated sinusoidal functions. We think of the argument always going from 0 to 2 pi, because that's what cosine or sine makes the cycle repeat. 2 pi is the key value. Okay? So we look at the argument and we say, let the argument vary from 0 to 2 pi, and then what input value will cause that argument to go from 0 to 2 pi? Okay, so here's a different one. What's the input? The input is t. What's the output? Sine of 3t. Vertical distance above the horizontal diameter. What's the argument? 3t. Okay, so here's the key. So how does 3t need to vary for g to go through 1 cycle? How does 3t need to vary so that g goes through 1 cycle? From 0 to 2 pi. Because that's what the sine, that's what 1 cycle of sine is. From 0 to 2 pi, it gives 1 cycle of sine. So therefore 3t needs to go from 0 to 2 pi. And so we can say, when we have the period, we were asking what time period will make 3t equal to 2 pi? What time period will make 3t equal to 2 pi? 2 pi over 3. So what's the period of g? 2 pi over 3, because it's the interval width of input, t, that causes g to go through 1 cycle. And how does it do that? Because it makes 3t go to 2 pi. And that's what sine needs for 1 cycle. So it's the value of time that makes 3t, the argument, go to 2 pi, so that sine goes through 1 cycle. Does it make sense? So you try this one. Go. Try this. What's the input? What's the output? What's the argument? What's the period? So what's the argument? 2/5 theta. And to find the period, we ask the question, how does 2/5 theta need to vary for h to have 1 cycle? 2/5 theta needs to go from 0 to 2 pi. And so then we say, for what angle theta will 2/5 theta reach 2 pi? It turns out to be 5 pi. Okay, so now based on the period being 5 pi and based on it being a sine curve, can you sketch h? Can you make a sketch of h? So the first thing you have to figure out is how you're going to label your y-axis, how you're going to label your x-axis. So how am I going to label the y-axis? What's the maximum? 1 radius length. Minimum? -1, okay? If it's just plain old sine, it's measuring radius lengths. We know in a circle, the highest radius length you can get is 1 above. Lowest is 1 below, okay? In terms of radius lengths. Okay? And then, how am I going to label the x-axis? In terms of pi. Should I do pi over 2, pi, 3 pi over 2, 2 pi? Is that how I should do it? No, we want to use our period, right? We know it's going to be based on our period. So let's go out to 5 pi, and then how are we going to split it up? Divide by 4, right? Because we know that our cycle, we can think of it most easily in 4 pieces. So first fourth, 2 fourths will be halfway, 5 pi over 2. And then whatever it takes to get that one. So there's different ways to figure out what that will be. You can do 3/4 of 5 pi. You can do 3 times your quarter cycle. You can add the quarter and the half together. Whatever it takes to get that. What will that be? 15 pi over 4? Did I do the math right? Okay, and now we're ready to draw it. So now we draw the sine. The sine at theta equals 0, where's the sine? Is it max, midline, or min?
Midline.
Midline, and then the first quarter cycle goes up to the max. Next quarter cycle, back to the midline, down to the min, back up. Because it's the vertical distance. Well, a combination of things. Understanding sine and then having done it so many times. Sine is vertical distance above horizontal diameter, starting from the 3 o'clock position, right? What's that?
And you could plug it in, but you want.
Well, you got to know it. You got to know it, yeah. So starting at 3 o'clock position, you imagine, what does the vertical distance do? Goes up to the max, back to the midline, down to the min, back to the midline. And that's what this is showing. Does that help? Yep. So if you ever forget, you just can redo it, knowing that sine is vertical distance above the horizontal diameter. Okay, can I erase? So now I want you to flip forward to page 295, number 2. So now what happens is, when the pedal starts, the tire valve is 1/4 pi clockwise from the 3 o'clock position. Okay, so the tire valve they don't start both at the 3 o'clock position. The tire valve starts at 1/4 pi clockwise from the pedal. Okay, so how can you describe the relationship? How would you, in words, describe the relationship between the tire valve angle and the pedal angle? So how would you just, as most simply as possible in words, describe what the tire valve is doing its angle relative to the pedal.
Would you say that it's a negative theta? Would you say if it's a pi over 4, is it like a negative pi over 4?
It's identical to the pedal minus the word pi.
Yeah, so how, what would you, yeah, exactly. So our, again, if our pedal angle is theta, okay, swept counterclockwise from 3 o'clock. So how would we write the, in terms of theta, how would we write the angle swept by the tire valve? Sorry. So the tire valve angle, he's offered up theta minus pi over 4. Agree with that? Is the tire valve angle always pi over 4 less than the pedal angle? That's what it is. Yeah, it's always that. So how would you describe that, just in words, without kind of that mathematical statement? So what's going on? How would you describe that? The tire valve is,
About an eighth of the way behind pedal.
okay, he said 1/8 of the way behind. So pi over 4, is that 1/8 of a circle? Yeah, it's 1/8 of a circle. And so that tire valve, would you say it's always that angle behind? Yeah, it's lagging behind, right? So that's the way we want to think about this. And that makes sense with the math, right? That angle is behind. It's less than the pedal angle by pi over 4. It's lagging behind. Okay? So now, what are they? Okay, so P is going to be our vertical distance of the pedal angle above the horizontal diameter, and T is going to be our vertical distance above the horizontal diameter for the tire valve. So this is the pedal vertical distance, and T is the tire valve vertical distance. So what is the function P? What function would give the horizontal vertical distance above the horizontal diameter of the pedal in terms of the pedal angle theta? That's just plain old sine theta, right? Just plain old sine theta. Okay? And so for T of theta, if we want vertical distance, then in general it's going to be what function? Sine. Okay? Of what angle? The tire angle, right? So if we want the height of the tire valve, then we need the angle for the tire valve, right? That's what we said, theta over 4. So if we want the height for the tire valve, we need the angle for the tire valve. So the question is, when we graph this, so we all know what sine looks like. Let's graph that for the pedal angle. Okay? So there's our pedal angle, and I'll just throw it up over. Okay, so the question is, what is this T going to look like if we're saying that tire valve is always behind 1/4 of pi, or 1/8 of the circle? It's behind. So here's theta increasing, right? So you think of theta increasing like this. So what will the tire valve graph look like if it's behind? If it's behind.
Would take longer.
Shift over.
Shift to the left.
Okay, so is it shifted to the left or to the right? If it's behind. So this one starts, and then when does the tire valve start its cycle relative to this one? Before or after? After. So is that shifted right or left? It starts after, right? It's behind. It's going to start after. So is it going to start back here, or is it going to start over here? Yeah, so if it's behind, it's going to start after, right? Think of the angle going by like this. It's going to start its cycle later, after. It's behind, which is to the right. Can you see it? You got to see that red graph consistent with theta minus pi over 4 because it's behind. So which one comes first? Which one starts and finishes its cycle first? Theta or theta minus pi over 4?
Theta.
Theta starts and finishes first. Coming later or coming after is the tire valve. It starts at pi over 4
So you
and
still use
finishes
that
later.
3 o'clock. You still use that 3 o'clock as the starting.
Think of it that way, yeah.
That's what I was thinking, I thought you would start the quarter by the negative.
I'm seeing them start at the same time. You're saying that you don't even bother.
But this is a function of theta. It's a function of the pedal angle. Okay?
And the pedal angle doesn't start till 3 o'clock position.
What's that?
And the pedal angle doesn't start till the 3 o'clock position.
It starts at the 3 o'clock position.
Okay, that makes sense. That makes
And
sense.
the angle gets to the 3 o'clock position later.
Yeah.
So according, in terms of theta, it's going to start and transpire later, and that's going to be right.
7.
So you should see that red graph. It's consistent with being
Later.
a lesser angle. It's behind. It's a lesser angle, so it's coming later. Okay? So look at, while I reset, number 3, page 297. Read number 3 and see what you come up with. Okay, so what's the tire valve angle?
6 readings. Counter.
Okay, so how could we write the tire valve angle in terms of theta?
Theta plus the high.
You're right, and signifying that that tire valve is what compared to the pedal? Ahead. It's pi over 6 ahead. Do you see that? So its angle is tire valve angle is ahead by a 12th of a circle, or pi over 6, and so its angle can be written as plus. It's ahead. It's ahead, so it's a greater angle. So while that one's 0, this one's pi over 6. It's ahead, so it's plus. When this one's pi over 6, that one's pi over 3. So the tire valve is always ahead, or it's a greater angle than that one. Okay, so how will it? Is it cosine or sine now? The same. Talking about horizontal distance. So what am I showing there? When the pedal is in the 3 o'clock position, what's happened with the tire valve? It's already started. It's ahead, right? It's already started. It's coming before that. It's ahead. So what's the shift? It shifts to the left, and so what I'm trying to do is make sense of this plus pi over 6. So how does plus pi over 6 make sense with that graph? That's what we're getting at. Because it starts before. it's ahead. Its angle is ahead of the other one, so it starts before. So here comes the angle. What comes first? Tire valve or pedal? Tire valve comes first, and then pedal starts. Tire valve is ahead by 5 or 6. Okay, you got written homework for Wednesday.